Good afternoon, Jan.
Hi, Michael. Good. Happy to be back.
Yes, good to see you back.
Yeah. You're
Excellent.
already on YouTube or not yet?
Yes, we are.
Okay.
Yep.
Okay.
Yep.
So, what do you have? What do you have for today?
Yes. Well, I have a question that came in uh, on the comments on the YouTube comments, and then
Mm,
yeah, also some feedback that came back from my the team at Improving that is working on a Jinaga-based application. And so these are both leading me to think about how to optimize the wire protocol that Jinaga uses. And yeah, I think there's a lot of opportunity there. So I wanted to walk through
Um,
some of those options.
yeah. So they wanted to change the protocol.
Yes. Yeah, there were um, some specific concerns, and then yeah, and looking closely at the protocol, I can see yeah, we can address those concerns.
Okay. I'm wondering what are these concerns?
All right. Well, let's start with. Um, let's see. Wait a minute. We're going to screens. There it is. Okay. Let's start with. Uh, this is kind of a weird way to present it, but okay, we'll see what we can do. So, yeah, this response came in uh, on
Mhm.
the fixing the queue episode. So, isn't this solution transferring the facts multiple times? And
Yeah.
yeah, I got to looking at it, and yes, it is. Um, so I'll walk back through that demo and show exactly why this protocol is transferring facts multiple times and what can we do about it.
Hmm.
Um, yeah, in my response here, I said that one possible optimization is to use Merkle trees. Um, and so that is something interesting to explore.
Hmm.
And then, in addition to that, now if you go out uh, to the Jinaga org, there's a project out there. Um, and on this project board, I'm tracking the various issues across all of the repositories that I am working on. So this includes Jinaga.net, Jinaga.js, Jinaga Server, um, yeah, where Jinaga Server feeds into the replicator. So I even have some issues here that are related to the private repos, like here Jinaga multi-tenant. So that's the private repo for the multi-tenant replicator as a service.
Hmm.
Um, so the uh,
Okay.
the things that I'm tracking here, um, uh, what came back from the improving team is that first of all they got an exception while loading a fact that had a null field from SQLite, and so
And you didn't have that one with the memory storage
correct,
store. Yeah.
yeah. They unit tested everything with the memory store. It was all working, and then they went to SQLite and then ran into this. And now the real problem with this one is that that null field is persisted in the database. I'm going to have to figure out exactly how it gets persisted. I thought I caught those on the way in, but
Mhm.
so that's persisted, and that means that anytime they run a specification that tries to load that fact back out, then they get this exception. So basically, that data set is stuck, and they had to switch to another data set within the um,
Mhm.
multi-tenant store. Well, SQLite, so it's intended for one tenant, but it's still it's still multi-tenant in nature. Um, so that one now has top priority. I'm going to put these two on hold. Um, and then this one just below it was kind of the core of the issues they were having with the protocol. So they found some HTTP 319 errors on both uploading and downloading when they had large amounts of data. To
Mm.
work around this, they've actually changed the model so that they limit the number of predecessors that a particular fact has. And so that, that sets off a red flag for me. I want application developers to be able to think about the domain and model the domain and not model the solution, not model how to make this thing work. So, yeah, if they
Mm.
model the domain and then if something doesn't work, then that's a problem with Jinaga. That's not a problem with the model.
So the tree got so deep that every time he downloaded all the preceding facts and all the predecessors.
Yes,
Mm-hmm.
yes. And so while looking into that and kind of comparing that with this this comment about about downloading the facts multiple times, it was like, yeah, there is some redundancy in there that can be squeezed out.
Okay.
So I can get rid of that redundancy. That will make this 319 less likely, but it won't completely eliminate it. What I also want to do is to use a chunking protocol. So you can do HTTP chunks, and then it'll put them back together on the other side, and then interpret the results.
Mm.
That way we don't run into any of these errors.
Yeah. Michael, one question in the in progress items.
Mm-hmm.
I only see one item there, the Blog Maui item.
Yeah.
And the Jinaga MT item is not there. Are you using an offline copy or?
No, that one is related to a private repo. So, yeah,
Okay.
that would make sense that it doesn't show that on the public facing board. Yep. Um, so yeah, the issue there is as I'm testing Blog Maui on my mobile, my actual iPhone, um, I've actually gone past the time that the refresh token should survive. So it's like, oh, I haven't tested this in a while, and open it up, and it doesn't do what it really should do. So so first of all, the refresh token was set to 1 month, so 30-day expiration time for the refresh token, and I went ahead and bumped that to 90-day. I mean, if I'm going that long between invocations of the test app, yeah, people will go that long before using an app. Um, so so that just means they don't have to log in again. But then the problem that it ran into is that the replicator returned, hey, I can't refresh that token. The token is expired, and so you were not logged in. But the mobile app it treated that as like a temporary error and said, okay, well, we'll try again later when you actually have some data to store, and then later on when you actually do try to store some data or you try to run a specification, then it says, oh, I can't refresh that. Well, we'll just kind of be in offline mode until we can fix that. Well, it's not going to get fixed unless the user manually logs out and then logs back in. So the intent here is to put the app into now a state where or basically log the user out automatically. So it's like, okay, the 90 days has elapsed, and the refresh token is not valid. So you're going to have to log in again. So we'll just
But
log you out to force you to do that.
but data that was stored before these 90 days.
Mm-hmm.
Oh, yeah.
Yep, that data is still there.
Mm.
Yep, that data is
That
preserved.
data will still be there and it will be synchronized.
Yes. Yes, so
Okay.
that'll still be in the queue, and those facts will still be related to the user. So if you log in as the same user as before, then you're going to be authorized to send those facts to the replicator. If you log in as a different user, this is actually something that I will want to. Let's go ahead and record this right now. Um, so if you log in as a different user, and then it tries to push those facts up from the queue, it's going to fail. Yeah, it's not going to be authorized. What I want to ensure happens is that we we keep those in the queue until you log in as the user that can actually save those. So this is probably a Jinaga. Oh, let's go ahead and add it to Blog Maui, and it might end up being support in Jinaga.net. That okay. So ensure that queued messages for another user are preserved and retried upon later login. So that we can start to gather information about that and get that ready. Okay. So yeah, I was working through those things, and then my team said, "Hey, we're going to be blocked pretty soon." So I said, stop. Let's work on these." And and so some of the things that I was thinking about, I still have that Merkle tree optimization. You got that issue out there. I haven't even refined it enough to really call it a backlog item yet. So I'm not really sure what that's going to look like, but we'll talk about some ideas. But before doing that, there are some things that I can do to optimize the protocol. So to demonstrate that, let's go back to the terrible chat app, which is not quite so terrible anymore. Okay. So I've got this running, and it is, if I go to network, it is going to be hitting the replicator as a service. So I'll look up the Jinaga topic, add that here, and you can see, first of all, it tries to save the Jinaga topic that it just created there. And the response is just going to be created, but this fact already existed. This is just the chat topic. Had some fields, had a hash, predecessors, had a type. So this JSON object, and we can see in the that's right here, view source. We can see that is how that is sent up to the server. So we'll return to save in a little bit, but then once it saves that, then it says, okay, I want the feeds for this specification. So here is that hash for the chat topic that I just created, and now run this specification and give me back all of the messages and their sender names. And so that results in these two feeds. So one of them is just going to be the messages, and the other one is going to be the sender names for those messages. And then you can see here it's going to fetch from both of those feeds. Excuse me. Yeah, so you can see this one is getting the chat messages, and this one is getting the sender names, but it comes back empty. So we won't worry about that one too much. So the chat messages, I think this is the first thing that we can really talk about doing some optimization. Let me copy this out so that we can see it in a better light. Okay, So we've got this JSON response, and you can see this is an array of fact references. And so a fact reference in the TypeScript code is type and hash. And so each one of these is of the type chat message because that was the particular tuple that it was selecting. That was actually part of the specification, is that I want chat messages here. If the tuple was selecting multiple labels, then you would get references from 2 or 3 different types, but still some small fixed number of known types. And then you get those hashes. So like, the first thing that you see is this is formatted. It's got all the white space in it. So that's one simple thing we can do to optimize is don't format it. Okay. And then the next thing that jumps out at me is all of this redundancy. We've got these types repeated several times. Mm-hmm. So if we think about just what is the unique information content of this thing, I think we can get this to just show up once, and then all of the hashes are unique. So we need each one of those to show up on its own. And then we've got the references and we've got the bookmark.
Michael, but with a good compression algorithm, all this redundant type information, they should be compressed to just a number or something.
That's true. That is true. Yeah, I think that's
yeah. That would leave us the advantage of if we disable encryption, we can just read it and debug it easily.
Mm-hmm.
And if we want it to be efficient, we encrypt it. We enable the encryption.
Yeah, that's true. Yeah, so I still do want to explore what can we do before it gets compressed. Yeah, if you rely upon the compression, you'll get quite a lot of benefit, but maybe not all the benefit that you could. So yeah, can we rearrange this, make it smaller even before it goes into compression, and then still keep it readable? And I think we can. Now, I did this manually before, but now I want to see if Copilot Chat can do this for me. So, what I want to do that if I group every one of the hashes under the type, I can convert that into an object. So, please, I always say please to the AI. Convert the references array to an object with a field name. Actually, I think JSON calls it property name. It'll understand either one. Is the type, and value is the array of hash strings. So now it should be able to. Oh, you can reduce. You can use the reduce function. That's not quite what I wanted. That is funny. Yeah. Can you apply that transformation to this data set? Okay. Yeah. Oh, it's just giving me the code that does that. Okay, well, that was an interesting idea, but I will go back to doing it by hand. So the idea that I had was if instead of an array, this is an object, and this is the field, then that can be an array, And we will have each one of these in here. Etc., etc., etc. And so, yeah, this is why I wanted chat to do this. It's usually really good at it, but now it thinks that I want it to write code. I guess I am inside of my code experience. Okay, so let's do one more thing here, and I think it is Shift Alt. Yeah, Shift Alt. Boom, does that, and then boom, do that. Very nice. Now I can move all this into the array. Boom, and put the comma right there. Okay. So that. Why is it having trouble with that? Oh, it thinks this is JavaScript. Nope. This is supposed to be. There we go. JSON. Okay. That might be why chat messed up. It thought it was looking at JavaScript. Okay. So that, I think, is still readable, and it's basically pre-compressing based on our knowledge of the protocol. So if we gave that to the compression, it would be able to find less redundancy in it, but it would still do something. I think, yeah, this is something to test out, but I think this would still compress to something smaller than the original. And we could even go one step further and just use single letters there. So that's what I'm thinking we might do for the feed response. Just tighten things up a little bit.
Yep. It's already a lot shorter.
Yeah. So the the purpose of the feed response, as it exists in the whole protocol, the whole back and forth, is that this is supposed to give the client information about what what facts are in the feed that it might want to ask about. So if the client doesn't know about these facts already, then it can turn around and call load. And in this case, oh wait, that's this one. Here we go. The payload. In this case, well, we'll go ahead and look at it parsed. Load was turning around and saying, okay, send. I don't know about any of these facts, so give me them all. So the load payload looks exactly like the feed payload, except it doesn't have the bookmark. So we can do the same optimization here. And the idea here is that if the client already did know about this fact, then it wouldn't have to call load. So, and this is what the one of the things that the commenter was talking about. So if I type another one here, so I send another message to the replicator. So so here I've got save. Oh, that's right. I didn't turn on subscribe, so we're not actually seeing the behavior. So because I'm not subscribing, this particular specification doesn't do another fetch to this feed. But with subscribe, it would keep that connection open and it would try to get more. So you see here it is saving well, it's doing 3 separate saves. Let's look at that. So saving the user again, it's saving now the username, and then finally saving the message. So I'm curious about that. Does it save the username again? Boom. And yes, it does. Okay. So yeah, I will have to figure out why that is happening. So that clearly is something that could just, that call doesn't need to happen. This is the only one that actually needs to happen. Okay, so that's another thing to add to the list. But now if it was subscribed, this chat message matches the specification, so it would have to come back in the feed. Let me see if I can turn on subscribe. Can I turn on? Yeah, I think I can turn on subscribe on this. So we'll go back to the code here. What have I got in here? Oh yeah, I was working on some. I think I was working on some versioning stuff. So let me save that. Working on versioning stuff. But let's say that I was doing a subscribe. So here I am on the topic, topics, no, not the topics, but the messages, the message list. And I've got the message list there, message pane. I think this is it. So right here I get the, you know what? I don't think I've exposed it through React yet. Okay, so that's the next thing I need to add to the list. So you can see here is the props. It's been a while since I looked at this code. So where are the references? Oh, that's right. Yeah, I've got the topics, the message list view model. There we go. Use message list. There it is. So, yeah, use state j.watch. Okay, I can do it. Good. So here I'm doing a j.watch in order to get all the messages. I could turn this into a j.subscribe. And now that should give me a subscription. So we can see that here it has already loaded some new code, and it's gone back to the feed. And if we look at the request, we can see the request headers except was application X Jinaga feed stream. Perfect. So it's now doing a subscribe on these endpoints. And it did that without even reloading the page. That's pretty awesome. I like this hot reload stuff. But the point is now, if we save a new fact, save a new fact, send that, we've got the save, but then look at here. We've got a call to load. And that's because this stream that was still open, if we take a look at the timeline here, we can see that that this is still going to keep on going. This call hasn't finished, but this stream returned a new fact, a new hash, and so we turned around and we did load. And so here's the payload. It's saying, all right, I just learned about this new hash. Tell me about it. Here is where it's sending back facts repeatedly. Let's take a look at the response. And we can see that we get back the topic, Jinaga. we get back the user with that that public key. Okay, yeah, I don't have authorization turned on this one. Okay, that's right. I didn't have to log into it. And then I get back the message with all of its predecessors. So let's take a closer look at that one. So new, and I want to make sure that you select JSON. Boom. Yeah. So the client already knew about the topic. That was one of the givens. So one thing that we can do is send back an incomplete graph. Basically, chop it off at the top. This fact is included because this one refers to it as a predecessor. And so if I knew that that I already knew about this fact, if the replicator knew, the client already knows about this fact, maybe it could just not return this, but still refer to it, and then the client would know what fact they were referring to. So I currently don't support incomplete graphs. The graph has to be a transitive closure, but that transitive closure means I have to send these predecessor facts back again every time. So that's really what the comment was all about. That solution is transferring the facts multiple times. Every time we get a new message, it refers back to the same topic that we already used to ask for those messages.
Yep.
But there's more redundancy that we can take care of. And this is where the Merkle tree thing comes in. So this user, there's nothing about the specification itself that tells the replicator that I know about this user. The user is not one of the givens. In fact, let me remind ourselves what did that look like. So here's feeds, here is the payload. So that's the specification that we are sending. So the specification starts at the topic. So here's the topic. I'm telling you, replicator, I already know about this topic. So, yep, you don't need to tell me about that. But there's nothing in here that says I already know about the user. So I'm just starting at the chat topic. In this particular case, however, I do already know about this user. This is me. I'm the one who sent this message. So the idea behind Merkle trees is that you can send some remote peer a hash of an entire tree, just one, just the hash of the root, and that demonstrates to the peer that you already know the entire contents of the tree. So if that tree is exactly the same on both sides, then the conversation's really short. It just says, yep, that's still valid. So the way that Ralph Merkle described creating these trees is you've got some logical structure for your data, and you build a tree out of it, and then you hash the leaves. So take their contents, compute a hash, and then you put those leaves into an array, and then include the information that's in the node just above them, and then you hash that collection. And you do that for the other second level nodes, and keep on going up the tree until finally you can hash the root and all of its children, and you get just one number. And so if anything inside of that tree changes, then that hash changes. So the first brilliant thing about that is that now if nothing is changed in that tree, then there's no further information that needs to change hands. The peer just says, yep, that's good. But then the absolute brilliant part of Merkle trees is if the hash is different, then you just go one level down, And you say, okay, here's an array of hashes for all of the child trees. And then the peer says, that one's okay, that one's okay, that one's okay. This one's different. And so in this conversation, you can keep on going down the tree. There's a lot of back and forth to make this happen, but then you get down to just the part of the tree that's changed. So this trades off a bit of latency to reduce bandwidth. So it's a brilliant algorithm by a brilliant mathematician, Ralph Merkle. We have him to thank for just about all of the cryptography that we use. He was the silent partner for RSA and for Diffie-Hellman, and so yeah, it's all Ralph Merkle under the covers. But so what we could do here is if we have some mechanism to tell the replicator that I already know about this user, then we could chop this off as well. This is the only new information. So if we could tell the replicator enough to get down to just that information, then I think we've optimized it. I haven't figured out exactly how to do this. I'm just inspired by the Merkle tree idea, and I think there's a path through there. In some respects, this hash is already a Merkle tree hash, because a hash of a fact is the hash of its fields and predecessors, where those predecessors are references that are themselves types and hashes. So, so you've got that recursive hashing mechanism. So it's really a Merkle graph rather than a Merkle tree, but the same basic idea. The problem is I don't know how, as a client, and specifically as a generic runtime, just a library that doesn't actually know your domain, how can that runtime know that this is likely to be a hash that shows up in the response? I don't know. I could take a look at all of the messages that I do know and take a look at their senders and say, okay, these are all the senders I already know about, and that's the only reason that you would be telling me about a user, and so here are all of the sender hashes. But that's a lot of information going up in order to avoid a little bit of information coming back. Once you've got, 5 senders, then the hashes themselves outweigh the user fact. So I don't know. There may be a Merkle tree solution in here, or there may not be.
Yeah, because if you have to keep a dictionary on the server side for each client, it's not going to be worth it.
Right. Yep. Yep. The server should remain as stateless as possible. It shouldn't even know how many clients are connected to it. The client should retain all that information. That's, for example, why the client keeps track of the bookmark. The client sends the bookmark every time, and then the server says, well, here's some stuff, and then here's a new bookmark, and then forgets about that client, and they keep track of their own bookmarks. But yeah, so
and can we do something with the bookmark in the opposite direction? A bookmark on the client.
I don't. Okay. So maybe the bookmark itself contains enough information that the replicator can understand what you already know. Okay, I think I see what you mean. Yes. Okay, so let's go back to this message here. So we see a bookmark, 309. So So the last time that this replicator sent us a response, it said the bookmark is 309. So that when I say here, I want to fetch from this feed, and you can see it's been timing out and starting a new feed, so that part is working. Oh, it just did it again. Boom. So whenever we fetch from this feed again, we send that bookmark 309. And you can see that the, well, this is a stream, so you can't actually see the response. But the response would have been an empty array of references, and the bookmark 309. But then it would keep that open. So we're telling the replicator we've read up to this point. The replicator has this entire feed of fact references. Here we have just the chat messages that are coming back. But the replicator knows what specification we use to create this feed. That is all the way back here in this payload. So it took this specification and it broke it apart, and it said, okay, one of them is just chat message, and then the other one is chat message followed by sender name. So this feed is just the chat message part. So the replicator knows you're looking at these messages. It can do the transitive closure of all those messages, and it says, okay, if you've read up to this point, you already know all of these facts. So yeah, I think that might be the key. That might be the key. This bookmark, this little tiny bookmark right here, is enough information for the replicator to do all that math and figure out that you already know about these facts. So yeah, the last mile is, this is the response from load, and as of right now, load doesn't say how it came to learn these particular hashes. But if it said, I learned about these hashes from this feed and this bookmark, then that would tell the replicator about that entire tree, that entire transitive closure. Nice. Nice. That's our way through. Yeah, so okay, so I will have to think through how to efficiently execute that logic on the replicator. That's a really nice trade-off. I like putting a lot of work on on the database, on compute, in order to save even a small amount of data transfer, because data transfer is by far the most expensive of those three things. So yeah, yeah, it's definitely the slowest. And then both sides have to get involved. You're taking up bandwidth from the consumer side. They're paying their cell provider for this bandwidth, and it's eating their battery. And if you can save them something by doing some extra work on this replicator that's running in the cloud on a really really good machine with a really fast database close by, yeah, why wouldn't you do it?
Especially the battery and the fact that if the connection is bad, if you have too much transfer to do, it will never synchronize.
Yeah. Yep. Yep, and that's ultimately the thing that's got my team worried, is that, okay, you get into one of these situations, and then just the overhead keeps it from making any progress. So the 319 that they saw was the first example of that. But they're like, yeah, I want to make sure that these are all ironed out. And I'm with you. I want to make sure of that too. Okay.
Because actually, if only the messages that are new are sent over the connection, then it's very little information. Eh?
Yeah. Yeah. And I think that actually puts us back on the positive side. Now, when we compare, what is it like to run a Jinaga application versus what is it like to hand code a RESTful application, using HTTP endpoints and JSON, and come up with your own projections, and just do all that by hand. I want to be on the side of Jinaga is easier, it's faster, it's less data going over the wire. I want to be on the side of there is no downside, and I think this might actually put us on that side, because this is crazy optimization that you would never do application by application. But if I can infer that optimization from the mathematics of specifications themselves, then always do it for you and always do it correctly, then there's no downside. I love that.
Yeah, because the way it is now with the whole transitive closure, which goes every time again over the connection.
Yep. That becomes a problem. But even before we get to the Merkle tree thing, there are some optimizations that we can do here, and so what my team was really focused on is these hashes. You can see a lot of times this, so this is a 512-bit SHA that's base64 encoded. So that's a lot of information. Most of the time, there's more data in the hash than there is in the actual fact. So you could send this in less bits than you can send that. And then here we're using that hash again in order to refer to the predecessors. So we've got these hash lookups that are happening inside of this array of facts. And it's an array so that we put this in topological order, and we know that the predecessors occur earlier in the array. So how can we get rid of some of these hashes? Well, one of the ways that we could do that is, well, these are in an array, so they've got indexes. If I just index into this array itself, then I can get rid of those hashes. So let's say that this particular fact reference here, that's just a reference to this first fact here, so just replace that with 0. And this one here, that's a reference to that one there, so we replace that with 1. Boom. So already saved us a lot of space and didn't destroy any information. The information is already there. It's like, yeah, that's an easy one.
Which is basically what a good compression algorithm would do.
Yep, but I can do this now with a little bit more, with knowledge of the domain and or the protocol, and give the compression algorithm a break. So that's a pretty easy one. But then the next thing that that hit me is the fact that these particular hashes here, sending them is redundant. When they get received either on the replicator or on the client, whether it's in JavaScript or .NET, the first thing the recipient does is hashes the fact and then compares it with the hash that it received. And if it's different, it rejects it.
Michael, I'm going offline for 2 minutes because there is a customer who needs an urgent call from me.
Okay.
I will be back immediately.
All right. Yeah, so while Jan is doing that, I'll go ahead and make the next optimization, and that is, let's just not send these hashes. Ba-ba-boom, ba-ba-boom, ba-ba-boom. So we've already sent enough information that the recipient can compute the hash. And I have enough confidence by this point to know that both the JavaScript code and the .NET code are computing the hash properly. And So what would happen if they don't compute the hash properly? All of the other back and forth, like here, whenever you call whenever you call load, you say, I want to load these particular hashes. These are hashes that the feed returned. So yeah, these are the responses. So the feed's still returning hashes. So these are the hashes as computed on the replicator. And so load is just parroting them back. If for some reason the client was computing hashes differently, then these wouldn't match, and the client would receive some data. It would store it, compute a different hash for it, and then when it tries to load again, it would say, "Well, I still don't know that because this is a different hash." So that would cause some incorrect behavior on the side of the protocol that had the incorrect hash computation. So I'm not too concerned about that. Testing will find that. But then also there's no attack vector. There's nothing that you could do with that to say get around the distribution and see data that you're not supposed to see. So I'm pretty confident that just doing that is a net positive. That it doesn't take away anything valuable, and it saves quite a lot of space. So we are now down to a pretty concise little protocol. So the let me check my notes and see what. There was one more thing that this might be going to an extreme, but wanted to give this a shot and see. So here are the notes, how I kind of did all this by hand. So here's an example. Here are some of the things we could do. Chunk the request, we talked about that. Use an array index instead of hash for internal references. Already talked about that. Don't format the JSON. Use protobuf. That is an option. Honestly, I don't know how much that will improve things over doing this. Some custom format. So let's suppose that, in fact, now that we can remove the hashes, we can do one more thing. Yeah, I want a custom format without hash. Now we can take this away. All of that. And that might be all that it takes. So if instead of sending JSON, I knew that each one of these facts was a type, predecessors, or a type, type, predecessors, and fields, then I could just send those three objects. One would be a string, the other two would be JSON objects. So, did everything work out? Yeah, and I think I see you back.
Yep, I'm back.
Yeah.
I'm back.
Yeah, everything okay?
Everything okay? Yeah.
Okay, good. Yeah, so you can watch back, but yeah, the next optimization was, since the hash is redundant, we don't even need to send the hash because the recipient is going to be computing it. And this is true both for incoming and outgoing. So yeah, coming all the way back to here where we saved. Here's our payload. let's get one of these more interesting ones, even though these shouldn't, yeah, like this one here. So here's a payload that's sending back, the topic, the user, and the message. You can see this is sending back the hashes for each of those things, and it's sending back the predecessors as hashes.
Yeah.
So we replace those with array indexes, and then we can actually just get rid of the hash inside of this, the body here, because the recipient's going to be computing the hash anyway, and it should be computing exactly the same hash.
Okay, so based on the indexes, they know the relationships
Yeah.
towards the predecessors, and then locally they can recompute the real hashes.
Mm-hmm.
Yeah.
Yep. So that gets
that's
us,
a very clever idea.
That gets us from that down to something like that.
Yeah.
So then the very next observation was, well, maybe this doesn't have to be JSON. Originally, I was thinking protobuf, and I think I want to compare protobuf with this custom format that I'm thinking about. So I documented the custom format here. Let's go ahead and transform it here so we can see what this one would look like. So so we know that we're returning an array of facts. So rather than making that a JSON array, let's just have each fact object. Well, I'll switch this back to plain text so that we don't get a whole bunch of errors. So we've got our type, our predecessors, and then our fields. And those can still be JSON objects, because this name here is the name that the developer gave it. So this is information that Jinaga itself doesn't have. The name here, facts, well, that's just a name that Jinaga gave it. So that name is not important. That can be thrown away for the custom format. But this name needs to be kept. So yeah, we're also throwing away the names type, fields, and predecessors, and they're just represented by the placement. So then we do 2 carriage returns to separate them, and we've got our predecessors, and then we've got our fields here. And even get rid of that space there. And then finally the chat message. Boom. And now we've got some interesting predecessors for this one. Yeah, maybe I should have given chat one more shot at this. I think, yeah, I don't know. I don't know that I'd have been able to describe this in enough detail for it to get it right. But we're almost done. Yeah, and then compress the unnecessary white space here. So yeah, that has turned into that, and it's the same information.
Eventually, we can go very far in that optimization.
Mm-hmm.
But I think if the transitive closure is already reduced by only sending the necessary facts, and then the hashes are left out and just the relationship by indexes, I think the reduction will already be enormously.
Yeah, I think so. There is one little wrinkle. Now that we're using indexes, the transitive, or the reducing based on the transitive closure of the givens, or based on Merkle tree, those would then be removed from the result. And so these, how would we tell it that particular fact that you know I already have, that's the one that is the predecessor. Um, so so there is some tension between those two. Um, it would be possible for the maybe I don't know. I have to think through with that bookmark optimization that you were just talking about. Um, um, it might be possible for both sides to understand the complete set that they are talking about. Um, the problem is so yeah the yep, with the givens. So that is a given.
I think I see what you mean.
Yeah.
We leave out the predecessors,
Mm-hmm.
but because we don't incorporate the hashes anymore, we replace them by an index,
Mm-hmm.
but we don't have the hashes anymore. We don't have a reference to that predecessor that the client already has. Is it that
Right.
what you?
Yep.
Okay.
Yep. Exactly.
So we would need of every predecessor that we leave out, we would need to have the original hash at
Mm-hmm.
least one time.
Yeah. Yeah.
Yeah.
So yeah, one possibility is to so let's get back to the hash for the chat topic. So there's this guy. So one possibility is that instead of this, we send this. Um, and so now it's like, yeah, I know that you already know about this fact. Here's the hash so that I can refer to it in the array. Um, is that less than that? In this case, I think it's actually more characters. In general, will it be more or less? That's in general, it could be less. It could be that that you are far enough down the graph that you can just refer to one predecessor up by its hash and not its predecessors, and so you've replaced several different facts at the top with one hash. That's possible, but I don't know if that's going to be the the yeah, this now we're entering the realm of the probabilistic. We want to make sure that for the most likely case, we're reducing the amount of data. So that's one option. Another option is that both the client and the server know that this was the given, and so if we were to remove it altogether, and then interpret this not as an array of two things, but really as an array of three things. So this is the continuation of an array where the first part of it was the transitive closure of the givens. So there's enough information there. They would both agree what fact number 0 is, but the problem is that the transitive closure does not impose a total order. It's partially ordered, and so you will come up with one topological order of that partial order, and so each side might come up with a different order.
Yeah.
So those indexes might not mean the same thing on both sides. So there is some tension there. So I think what I would like to do is make these optimizations. I think the optimization of not sending the hash and using the indexes is compelling enough that even if it creates so much tension that we can't do the other optimizations, it's probably a good thing to do, and then see if if I can prove that that sending the hash. Oh, I've already exhausted my paste buffer or my undo buffer. But yeah, if sending the hash, there it is. in general is a savings,
Mm.
and then yeah, only in these small cases like this one that does it cost, and then it doesn't cost very much. In that case, then um, maybe I can take this next step, um, and then further take a look at the Merkle tree thing and see if I can use the bookmark in order um, to understand that you already know this, and therefore I can just give you the hash. So I think taking it in that order, um, I will I will get the biggest win first. Give that to my team, and they can continue, um, and then try to get smaller wins. So, yeah, that as opposed to yeah, not just that, but that. So that whole thing.
Mm. Look, it's a good strategy, and let's see what both ways result in.
Mm-hmm. Yep.
And perhaps in the end, um, the replicator might find out which of the optimizations would be for every case the most effective one.
Oh, I see. Yeah. So even take that extra
Mm.
load on the replicator where it can yeah it can try a couple of things out and say, oh, this is going to result in an 80% um, yeah, of the data versus that one, so a 20% savings. So
Mm.
yeah, let's go ahead and send this one, and the client can understand either. Yeah, yeah, yeah. That makes sense. Okay, so yeah, we've got some work to
A
do.
lot of I will see coming in a lot of GitHub notifications, I think, this week.
Yes, indeed.
Yeah.
Yep. So yeah, you can follow along up here,
Mm.
and we will knock these things out.
I have the screen open now, so okay.
Excellent. All right. Yeah. So thank you so much again. Yeah, the progress is going well on the book.
Mm.
So probably I'll probably get through with um, the tech review revisions this next week. So if you've got any feedback on the final chapters that you're looking at, then I can incorporate that. Um,
I will I will see for
so
chapter 13 because that's most likely the one where because it's completely new.
mm-hmm.
Um, I will try to finish that one.
Yeah, yeah, very good. Okay,
Okay. See you next week.
indeed. See you then. Thanks so much, sir.
Okay. Bye bye.
Bye.